My cat Onyx gets excited about her new mouse toy. Molecules can get excited too. They can vibrate a lot, that's a vibrational excited state. They can rotate faster, that's a rotational excited state. Or they can be electronically excited, where the electrons move to some different arrangement that's higher in energy. And it's that last category that I want to talk about a little bit today. All right, today I'd like to tell you a little bit about excited electronic states, what they are, and how we can model them using computational chemistry. First off, what's an excited electronic state? Well, if you have a UV Vis spectrum, which is something we take not infrequently in chemistry, that spectrum is dominated by electronic transitions. The molecule is undergoing a transition from one electronic state to a higher electronic state, and it absorbs photons to be able to achieve that quantum jump up into a higher state. These typically occur in the 1 to 12 electron volt range. If you like wave numbers, that would be something like 10,000 to 100,000 wave numbers. So it's a pretty large energy transition, especially compared to other things like vibrations or rotations. These electronic transitions involve rearrangement of electrons, typically valence electrons. If you have a transition on the lower end of this range, that's typically going to involve unsaturated compounds, molecules with double bonds. You may have conjugations of multiple conjugated double bonds. And the more conjugation you have in general, the lower the energy required to hop up to that next electronic state. If you have higher energy transitions, more like the 50,000 to 100,000 wave number range, then that will include valence and also Rydberg transitions. Now, what's a Rydberg transition? A Rydberg transition is one where you hop from a valence level that the electron is in into some big orbital that is far away from the nuclei, and it's typically a very large diffuse orbital. And if I hop up into an orbital like that, that's called a Rydberg state. And it kind of roughly looks like a molecular cation with a loosely bound electron that's kind of orbiting around at a significant distance from the nuclei. If I'm at 100,000 wave numbers or more, these are high energy transitions that often lead to an ejection of the electron. All right, so just to show some example UV Vis spectrum from the literature, you can see that I have peaks that are kind of broadened, so they have some width to them. Unfortunately, this width is not easy to compute with quantum chemistry. We normally just compute a so-called stick spectrum, where we expect a transition here and maybe a transition here with no width. Sometimes in our computations we can apply some artificial Gaussian broadening to make it look more like a realistic spectrum. This broadening in principle can be computed with more sophisticated techniques, but if I just use canned software and a standard excited state calculation, I'll just get the so-called stick spectrum. But I can get intensities in principle. Those might require a little bit of computation to compute the intensities, but that's something that a lot of the standard software will produce for us. So we'll have where a peak is and how high the peak is, but not how wide the peak is in general. Now, how would I compute the intensity of a peak? This is the formula for that, which is not overly complicated. This is so-called oscillator strength, FPQ, between two electronic states, P and Q. So I'm making a transition between P and Q, and that has a so-called oscillator strength to it, and the intensity is going to be proportional to this oscillator strength. And it just depends on some constants, and then the energy difference between the two states that are involved. And then this guy, which is called the transition dipole moment. It's a vector because it's a dipole moment, so it has x, y, and z components. And I just compute the matrix element of the dipole moment operator in between states P and Q, and take the absolute value squared of that, and that will give me the transition dipole moment. And so that lets me have the intensities, which are, of course, very valuable. How do I think about these excited electronic states in terms of some diagrams or something? Well, you could imagine this kind of picture representation of where the electrons are in different orbitals. So here we've occupied the lowest energy orbitals, and then light comes in, and that gives us some additional energy, and we can capture that photon and convert its energy into a quantum jump, allowing us to place an electron in a higher energy state. So on the right hand side, I've got the excited state where I've promoted this particular beta electron from this highest occupied molecular orbital to this lowest unoccupied molecular orbital. And of course it takes more energy to do that, to go hop from this level to this level, and the energy is coming from the photon that I've captured and has been absorbed. Now, one issue, you could say, well, I could just compute the energy of this Slater determinant, and then I could subtract the energies one from the other, and then that would tell me what the excitation energy is. In principle, yes, but in practice, no, because most Hartree-Fock and DFT programs don't know how to compute the energy of an open shell singlet like this, where the electrons are not paired up, and I've promoted one but not the other to some higher energy state. In fact, in general, the programs have been written to try to always fill the orbitals in such a way to give you the minimum energy. So if you were to try to get something like this, unless you put in special constraints or something, the program is going to want to fall back into a configuration like this because it knows it's lower energy. So how could you try to get something like this? Well, in principle, programs could be written to handle something like this, but in practice, generally, they're not. Now, if it were an excited triplet state, so suppose instead of one spin up and one spin down, I had both spins up, well, then it looks like the lowest possible triplet state. So if I had a spin crossing from a singlet to a excited triplet, the triplet might be the lowest possible triplet, and high spin calculations can be done. So that could be done as two so-called ground state calculations. So how am I going to go about this? And imagine a different scenario where maybe I have a radical and it absorbs light, and the unpaired electron hops up. Could I model something like this? Again, no, because the SCF procedure will keep tweaking this orbital to give you a minimum energy, so it'll wind up looking more like this again. This is sometimes called variational collapse. So that can be a problem to model. Let's just talk about what do these excited states look like in terms of expansion of determinants. So here's a CH molecule, CH radical. The ground state, often denoted by X, is a doublet pi state. It's a doublet because there's one unpaired electron, this radical electron. And I could generate various possible excited states from this ground state by promoting one of the electrons. And there are several possibilities. Here's one, the A quartet sigma minus state. It looks like a single Slater determinant with this particular electron configuration. What I've done is pop an electron out of the third sigma bonding orbital and popped it up into a pi orbital. So I have two unpaired electrons in pi orbitals. But that is a high spin quartet where I have three unpaired electrons compared to only one in the ground state. But this could be represented very well by a single Slater determinant. In fact, the whole wave function looks like basically one determinant with a coefficient of 0.99 on it. So that one could be adequately done by just a single Hartree-Fock or DFT calculation on this one determinant, and I'd get a very reasonable answer for that because it's the lowest quartet. Now the next quartet, this C quartet sigma minus state, is unfortunately a mess. It's a combination of several Slater determinants. The first two have coefficients of about 0.5. Then there's another one with about 0.4. I'm going to have to include at least those three determinants, and I probably really ought to include this one, which has an unusually high weight of 0.26. So the electronic nature of this state is spread out among at least four important Slater determinants, and then there's no hope of doing that with a single determinant method like Hartree-Fock or DFT. I'm going to have to do something special to get this one. And then again, just another example, another doublet state, this A doublet delta state, is a linear combo of two determinants that are both very, very important with weights of about 0.69. So frequently, excited electronic states are combinations of multiple Slater determinants with large weights, and then that implies a standard Hartree-Fock or DFT approach won't work. I'm going to have to do something a little different, either some kind of multi-configurational approach or a specially constructed excited state method, and that's kind of what I want to talk about today. This is just an example of a potential energy diagram, again for the CH molecule, to show you that there can be multiple electronic states. Some of them can be kind of crowded and even cross each other. If they have different symmetries, they're allowed to cross. So I can have kind of a mess of these things, and you see it gets more messy as I go to higher energies and slightly longer bond lengths. These things really tangle up with each other. So it's complicated. Now there are three different ways to measure the excitation energy of an excited state. So let me illustrate those with this diagram. Here I've got the ground electronic state. Here I've got the excited electronic state. And notice that in this diagram, the excited electronic state prefers a slightly longer bond length. So my x-axis here is a bond length. You could think about this as a diatomic molecule or something. If I'm in the ground state, normally I will be on average near the minimum of the potential well, even if I've got a little bit of vibration, like the 0-point vibrational energy. It's symmetric about the minimum of the well. So when a photon comes along, then I'm going to absorb vertically from my ground state to this excited state, and this will give me some excited vibrational energy as well. Because I land here instead of at the bottom of the well, so I wind up in some excited vibrational state in general, corresponding to this point on the excited state potential surface. And that's the vertical excitation energy. I could instead measure the so-called adiabatic excitation energy, which is from the very bottom of this well to the very bottom of this well. If I want to measure that, then I have to know what the minimum on this excited state potential surface is. So I would have to minimize with the geometry optimizer the excited state surface. And some programs can handle that and others cannot. It depends on the details of the program and the level of theory you want to employ. And then I also have one more energy difference here in pink. That's delta E00. That's the energy difference between the 0-point vibrational level of the ground state and the 0-point vibrational level of the excited state. And you could imagine if I excite into the excited state and then it has an opportunity to maybe collide with other molecules and shed some of that excess vibrational energy, it might settle down into the 0-point vibrational level of the excited state. And so then this quantity might be relevant. Again, to compute that one, I would also need to know what the excited state geometry optimum was. Now, what kinds of excited states do I have? Well, I have valence states where I move an electron from one valence orbital to another valence orbital, like a pi star or into pi star transition. These tend to be lower energy compared to other ones. I have these Rydberg states where I move an electron into a very big diffuse orbital. I've almost ripped it off, but not quite. It kind of hangs around out on the outskirts of the molecule. Those can be a little bit higher energy than some of the valence states. And I can have core excited states, which are the highest energy states, where I rip out a core electron and move it either into a Rydberg level or a valence level. And just a little bit more about valence states versus Rydberg states. Experimentally, valence states often appear as broad features in the spectrum, whereas Rydberg states can be a sharp transition without much width to that peak in the experimental spectrum. Rydberg transitions often occur in a series that can fit to a formula where the frequency of light times Planck's constant equals some energy epsilon sub I, which is the ionization potential to rip an electron out, minus, doesn't take quite enough energy to rip the electron all the way out because it's hanging around, so the energy gap is not quite the ionization energy, but a little less than that. And the difference is the Rydberg constant minus parenthesis squared n minus delta, where n is a so-called quantum number and delta is the so-called quantum defect. So this is a very nice structure, and if you see a series of lines that would fit to this, then it tells you you do see a Rydberg series. And the series simply corresponds to the fact that this loosely held electron that's on the outskirts of the molecule can be in a certain quantum level or the next quantum level or the next quantum level. There are levels that are bigger and bigger and bigger, but their energies are not very different. Why? Because this orbital that they're in is so large that slight differences in the radius don't change the energy very much. They're held by just very little energy, actually. So it's kind of like in a hydrogen atom. As you go from to higher and higher energy levels, you remember they converge towards an energy of 0 in the limit that I would have an infinitely large principal quantum number in, and a similar thing happens here. So just to reiterate that a bit, this is the energy of the incoming photon, this is the energy required to rip an electron off all the way, and then I need a little less energy than that because it's not ripped off all the way, and I have principal quantum number corresponding to that big orbital n and a correction factor delta. So pictorially, my molecule starts off where I'm in some nice closed shell ground state. Light comes along and promotes the electron, so here comes light. I hop that electron up into some higher energy state. Now to rip it off all the way would be epsilon, where I go up here, but I'm not necessarily going that far. And that difference is this minus r over n minus delta squared factor. And so now I wind up with my electron in a higher energy orbital that's some big diffuse orbital, and the molecule looks like an ionized molecule plus some loosely attached electron in some big diffuse orbital. Now let me reiterate a little bit more about the multi-determinantal nature of excited states. Suppose I'm in a pi to pi star excited state. Well, there are at least two completely equivalent ways to write this state, either the alpha electrons here and the beta electrons here, or vice versa, beta here and alpha there. And these should have exactly the same energy, and so their contributions in the total wave function should have equal weights. And if I tried to describe my wave function just by one of these, I'd be missing half the wave function. So this is the classic problem of a so-called open shell singlet that standard Hartree-Fock or DFT programs are not written to handle if you were trying to treat this as a ground state problem. However, it doesn't necessarily mean that I must use a multi-determinant or multi-configurational method like CAS-SCF. We can apply some tricks, and knowing that this is some excited state from some closed shell reference, I can get at this in a different way. So I can use so-called single reference methods, but they need to be excited state methods, not ground state methods. So let's talk about single determinant descriptions of excited states. So suppose I have this state where I've promoted an electron from orbital I and orbital A. I've chosen to promote the beta electron in this particular picture, and I can denote this with this ket phi IA, which means I've taken an electron out of orbital I and put it into orbital A. And I could call this an excited determinant or a substituted determinant, and we've seen this notation in talking about correlated methods, post-Hartree-Fock methods. I can describe this easily enough by a single Slater determinant, where I've just taken one of the columns of that determinant, which used to have this electron in orbital I, and replaced that column now with putting the electron in orbital A. This determinant would roughly describe the excited state, with the caveat that I'm missing its sort of a mirror image where I flip alpha and beta that I talked about on the previous slide. But certainly I can think about this Slater determinant as an approximate representation of an excited electronic state. And the only problems are really that A, the orbitals I might have gotten from the ground state Hartree-Fock calculation may not be the best orbitals to describe this open shell singlet excited state. So the orbitals may not be optimal. And B, I do have half the wave function because I'm missing the other mirror image pair. And in fact, there may be other determinants that maybe are not quite as important as this one or its mirror image, but that might still have a significant weight. And so that's the other issue with trying to think about this as an excited electronic state. So what I do need is some kind of multi-determinant expansion for excited states, not just this determinant, because this is just not going to do it for us. So how am I going to get this multi-determinant solution? Well, first off, let me remind you, when we solve our electronic Schrodinger equation, H psi equals E psi, it has multiple solutions, which I've highlighted with this superscript I. And what we're really trying to get here is one of these excited solutions. So not the lowest energy one, but some higher energy one. And there are multiple solutions, just like we saw in that potential curve of CH. There are quite a few electronic states. So we're trying to get one of these higher ones. How can we do this? If you have a method to solve the Schrodinger equation, which will give you multiple roots, then just do that and get one of the higher roots. For example, configuration interaction. We normally, for computational efficiency reasons, just get the lowest state, but we're diagonalizing a Hamiltonian matrix effectively, and that procedure could be done for the lowest 10 states if you wanted, and that would be perfectly fine. and those other roots would approximately describe excited states. So I could do something like that, or I could use some kind of response theory formalism. Now, if I do response theory, what does that look like? Well, I imagine that the molecule sees an incoming photon, which we're going to model as an oscillating electric field. And if I do that, I can say, well, how does the molecule respond to that oscillating electric field? And I would need to know the frequency-dependent polarizability of the molecule. And that's approximately, here's the polarizability alpha, an average value in brackets, and at some incoming frequency omega. I can do this approximately with the sum over states that are not the state that I start in, and just look at these transition dipole moments between the initial state psi 0 and other possible excited states psi I. Take this transition dipole moment squared and divide by omega minus the energy difference between the state I'm in and these excited states. So this is so-called sum over states expression. And I can identify excitation energies, delta E, as the difference between where I'm at and the excited state energy, just from looking at the poles of this alpha. So if I can compute this quantity and find its poles, then that tells me what the excited state energies are. Now, so how can I do this practically? Well, the simplest thing I could do is so-called configuration interaction singles. So let me remind you, that's one where I take my Hartree-Fock determinant and I form all possible ways to excite one electron, that's the singles, one electron, from this determinant. So if I had, say, 4 electrons and 4 orbitals, I could move this alpha electron here, I could move this alpha electron there, I could move this beta electron up to here, that gives me this one, and so on and so forth. So I have several different ways that I can rearrange these 4 electrons among these 4 orbitals if I move a maximum of 1 electron. That's a single excitation. This is the simplest possible thing you could do. If I do the configuration interaction singles and then form the full Hamiltonian matrix formed by all of these possible determinants and diagonalize that and get multiple roots, that will give me the different approximate solutions for the excited states as eigenvectors of that Hamiltonian matrix. And because I've included all of these different determinants, I have all the necessary determinants to describe open shell singlets. For example, here I've got this one, and I've got his mirror image pair here, and here I've got this one, and his mirror image pair there. So I have all of these determinants in my expansion, and configuration interaction gives me a linear combination of determinants with different weights on them. So I can weight these however I want, and I've got all the ones I need, which is great. The problem is, because I only have single excitations, I don't have any dynamical electron correlation effects, and so the quality of this for the excited states is poor. Sometimes people talk about this as having essentially Hartree-Fock quality for excited states, but not more. So it will work and you'll get solutions, but the accuracy of the solutions may not be very good. Just diagrammatically, what the CIS matrix looks like is I have the interaction between the Hartree-Fock reference and itself, E0. This is just the Hartree-Fock energy in this upper left-hand piece. That's a single number. And then I have a big matrix where I have all the singles going down the rows and all the singles going across the columns, and I work out these matrix elements using the Slater rules, so that's easy to work out. And I can fill in the different elements of this matrix for however many singles there are along the rows or columns. Now, the interaction between the singly excited determinant and the reference is by definition 0 if I have Hartree-Fock orbitals by the Brillouin theorem. So I don't need to bother to compute the rest of this row or the rest of this column. That's going to be zeros. If I form this matrix and diagonalize it, and there are various efficient ways to do this, I get excitation energies that are not very accurate. You might have an error that could be 1 electron volt, or maybe even a little more. which is not that great given that the excited state energy might only be 2 electron volts, so you might be making a large relative error. I can correct this approximately for dynamical correlation using the CIS parenthesis D approach of Head-Gordon and coworkers, and that can reduce my errors by something like a factor of 2, which is a big improvement, but that may still not be accurate enough depending on what you're doing. Could I do CISD for excited states? That sounds like a good idea, because then I have dynamical correlation by including double excitations. Yes, that for sure will give you dynamical correlation for the ground state, and the ground state would be described quite accurately. But the problem is that accuracy for the ground state doesn't translate to the excited states. Because if I needed to describe dynamical correlation in the excited states as well, then I would need double excitations for those, but those states are already singly excited determinants with respect to the reference. To get double excitations out of a single excitation, I would need up to triple excitations, which by definition are not included in CISD. So the problem is that CISD does a pretty good job of describing the ground state and a less good job of describing the excited states, and that means on average you push down the energy due to electron correlation for the ground state, and you only make a minor improvement due to all the mixing of the determinants for excited states, and your energy gap between the ground state and the excited state is too large because you're doing too good a job on the ground state relative to the excited states, and the stabilization you get from the doubles is mainly going by pushing down this one and not so much improving this one. So the energy gaps all increase. And so you get terrible excited state energies, and it doesn't work, unfortunately. What about density functional theory? Well, I can use linear response on top of density functional theory in what we call time-dependent density functional theory, or TDDFT. And this leads me to a set of equations, the Cassidy equations, that can be a bit complicated to solve, but they can be solved. Sometimes people make a simplification to those equations to make them a little easier to deal with, and that invokes what's called the Tam-Dankoff approximation. And generally that's a good idea because I often get excitation energies that are just as good as the original Cassidy equations with simplified equations. So you're not required to use the TDA flavor of TDDFT, but a lot of people do, and it seems to work fine. I won't go through the details of how that works because it's a bit complicated, but let me say a bit about how accurate it is. If I have valence states, I get them correct within about 0.3 electron volts, which is not bad. I have to watch it if I have Rydberg states or charge transfer states, where I transfer charge from one part of the molecule to another part of the molecule. And that's because DFT in general is using some kind of exchange interaction which should fall off with respect to distances with a potential of -1/r, but doesn't unless I take special precautions like using asymptotically corrected functionals or similar techniques, or range-separated hybrids. If I'm not using one of these techniques, I can run into trouble if I have Rydberg states or charge transfer states. What about wave function methods? Well, I already mentioned CISD doesn't really work. CIS works but gives large errors, so what else could you do? Excited state CISDT or something is going to be very costly. Your best bet is to move on to equation of motion coupled cluster. Equation of motion coupled cluster is a way to get at excited states using a coupled cluster formulation. So it's excited state version of CCSD. This one will treat excited states at a similar quality level as the ground state, unlike blindly using CISD. So what you do is you solve your normal CCSD equations the way you always do for the ground state. That gives you a set of T1 and T2 amplitudes describing the CCSD wave function. Nothing special about that. Then I do some stuff. I transform the Hamiltonian using a so-called similarity transformation using these T1 and T2 amplitudes determined for the ground state. Then I do what looks kind of like a CISD, but on this similarity transformed Hamiltonian using the couple cluster amplitudes. And that generates a set of singly and doubly excited states out of the CCSD ground state. And this works quite well for singly excited states where I promote one electron. I get values within about 0.2 electron volts of experiment if I use a decent basis set. And even if I have a double promotion of electrons, which is hard to describe by many methods, this can work okay with EOM-CCSD. I won't derive it or anything, but just to trace through a few of the equations. My wave function looks like a reference Hartree-Fock determinant hit by e to the t, just like in normal couple cluster theory, and also hit by this operator R, which is new for excited states. What is that? R is a linear excitation operator that gives you your reference determinant, singly excited determinants, and doubly excited determinants. So very analogous to CISD or something. And when you apply this operator onto phi 0, you get the reference determinant with some coefficient, singly excited determinants with some coefficients, doubly excited determinants with some coefficients. And the only trick is that I'm not applying R directly to phi 0. I define it this way so you can see what it does, but I actually apply it to e to the t acting on phi 0. So I'm applying it to the CCSD wave function, not just the reference determinant. Now I can do a little interchange trick where I actually, instead of literally doing it this way, I do the similarity transform Hamiltonian, h bar. What's that? Here's the similarity transform. I take the h operator, put e to the t on the right, e to the minus t on the left, and then I can put R after h bar and apply it to phi 0 and do this kind of Schrodinger equation. And so that's what I do, which I kind of described as doing CCSD first to get the t amplitudes, do the similarity transform, and then apply this linear excitation operator to get the excited states. There are other approaches. I'll just mention a couple things real quick. First off, there's not an excited state in MP2, unfortunately. If you started deriving something like that, you might wind up with CIS parenthesis D, which I already mentioned. Also, it's difficult, it's not clear how to derive a excited state version of CCSD parenthesis T, our favorite gold standard of quantum chemistry. And so there's not a clear-cut winner in defining what would be equation of motion CCSD parenthesis T. Some attempts to do this have been published in the literature. There is something called CC2, which is kind of intermediate in quality between MP2 and CCSD, and you can do excited state versions of that, so that's an option. And similarly, there's a more exact version called CC3, which is not quite CCSD parenthesis T, but it also has an excited state version, EOM-CC3, which is good to know about. Now, I did mention the excited states tend to be multi-configurational in nature, so can I use MCSCF or CSSCF? Sure, I can do that. I just get the excited states as higher roots of the CI when I do the MCSCF. If I have a good active space, I can treat ground states and excited states with similar qualities. I can get decent results, but not very accurate results unless I include some treatment of dynamical correlation, which I don't have in plain MCSCF or CAS-SCF. So that would require me to do some kind of CAS-PT2 or multi-reference CI. There are semi-empirical approaches to excited states. There's the famous ZENDO, named after Mike Zerner, which is an excited state version of ENDO. But I don't see these used as often anymore because TDDFT has gotten efficient enough that it can be applied to pretty large molecules, and so that is more commonly seen now. Now, if you want adiabatic excitation energies or nu00 or E00 excitation energies, I need to get the excited state geometry. Can I do that? Well, I would need analytic gradients for the excited state if I want this to move efficiently. And they have been derived and coded up in some programs for CIS, CIS Princess D, time-dependent DFT, CAS-SCF, CAS-PT2, and even EOM-CCSD. So this is a good thing. You can run into technical problems, though, because you may have excited states that cross each other, and the program may get confused and start hopping on some other surface and go off in some direction you didn't expect. So you have to be careful as a user. And that's all I had to say about excited state methods. I hope this gives you a good overview of what excited states are doing in terms of electronic structure theory, in terms of determinants, and a little bit about what are some of the methods that are available for you if you want to compute some of these excited states.